Welcome back to the second lecture on Athena. So yesterday I gave you an introduction to the basic algorithm, and I managed to have a look at Patrick Hennebel's slides online and noticed that yes, indeed, much of what I covered he'd already talked about, but in much greater detail, so that's good, that there's significant overlap and no conflict between what we're teaching you in this overall Godunov schemes. So in my remaining 4 lectures, I want to move beyond the basic numerical analysis to talk about today grids. In particular, I'll focus on extensions to curvilinear coordinates, so cylindrical coordinates in this case, say something about spherical polar coordinates, and also static mesh refinement. And then tomorrow I'll talk about extra physics, adding extra physics to the algorithms. And Thursday, radiation hydro, and Friday, a conclusion of applications. So today, first of all, I want to point out that there's alternatives to using structured meshes. I want to say something about Galilean Invariance of grid codes, because you may or may not be aware of recent interest in moving mesh methods and whether or not fixed Eulerian grid codes are Galilean invariant. So perhaps against my better judgment, I thought I would wade in and say something about Galilean invariance of grid codes. Then I'll, as I mentioned, talk mostly about cylindrical grids and static mesh refinement for the last part of the lecture. And again, I know it's early in the morning, 9 a.m. You may be half asleep, fine by me, but if you do have questions, feel free to interrupt me. I would much rather answer questions than just drone on at the front. So please interrupt me if I'm going too fast or anything doesn't seem to make any sense. So first of all, structured meshes. What does it mean? I mean, Athena uses a regular structured grid. That means to say that I showed this picture yesterday. You know, the variables that we're updating are stored in a regular fashion on the mesh. The vector of conserved quantities, mass, momentum, and energy is located at cell centers, at the geometrical center of the cell, whereas the components of the magnetic field are located at the corresponding normal faces of the grid cell. And then the fluxes that are used to update these quantities, in the case of the cell-centered quantities, they're located at face centers, whereas for the magnetic fields, the fluxes are the electric fields located at the cell edges, at the corners in 2 dimensions. And then each of these cells is replicated in a regular fashion across the entire mesh. That's what I mean by a regular structured mesh. And this has lots of advantages, both from a numerical analysis point of view, because you have a regular structured mesh, then you can get fortuitous cancellation of truncation error, which can make your scheme higher order at relatively low cost. And moreover, implementation is very straightforward. You can create arrays of these quantities. So in Athena, we create 3-dimensional arrays, which are pointers to pointers to pointers. And the compiler can optimize that fairly efficiently because the data is all contiguous in memory, and access to memory is in a very, very regular fashion. You're sweeping across the mesh in a very regular way. So the greatest advantage of structured mesh mostly comes in performance and in implementation. It's much, much simpler. But there's many other ways you could solve the equations, difference the equations. You don't have to use meshes at all. You could use spectral domain. You could solve the equations in the spectral domain. You could Fourier transform the equations and replace the spatial mesh with a discrete mesh in Fourier space, for example. Rather than having dx, dy, dz, you have delta kx, delta ky, delta kz. An entirely different approach, which has its advantages and disadvantages. You could use an unstructured Eulerian mesh. So what do I mean by that? So as I just mentioned, Athena uses a regular grid in 2 dimensions of cells. An unstructured mesh is just what the word means. You know, a collection of cells which have no regular pattern, no necessarily regular shape. You can use any arbitrary discretization you like and still have a finite volume algorithm that updates the equations in a conservative fashion. These methods are very, very popular for engineering problems because they allow for complicated shapes to be mapped easily. It's difficult to map, say, the shape of an airplane or the shape of a ship hull to a regular structured mesh, but for an unstructured grid, it's very easy to make extremely complicated shapes and treat boundary conditions easily that way. So they're very, very popular in engineering. Question?
Is there any advantage to a completely unstructured mesh over like a Illinois or a Voronoi tessellation?
That I'm not an expert on. I think the Voronoi tessellation actually is a very nice way of sort of optimizing the mesh every time step. So it seems like that's an advantage to me than a fixed. I mean, I guess if you're doing an engineering problem and you have a shape that's fixed for all times, then the Voronoi tessellation may not have any advantage. If you have a dynamically evolving flow, then this tessellation is really an attractive way to go, seems to me. Okay, so you could also use Lagrangian meshes where the cells are not fixed in space, but they're allowed to move around and follow the flow. That's a great way to go to 1D. In fact, in 1D, I think Lagrangian is always the best way to go because it adapts automatically to the flow. But the problem with Lagrangian is in multi-dimensions, if your flow has vorticity, then the cells get wound up in complicated ways. The grid cells get very, very stretched. And so that's always been the disadvantage of Lagrangian methods. And that's why these moving meshes have become more popular, because you recompute the mesh every time step to get rid of all of those complicated shapes that you produced by Lagrangian meshes. You can abandon the mesh completely and use SPH methods, as Paul was telling us about, and Will could tell us about more in a little bit. And then finally, you can use so-called arbitrary Lagrangian Eulerian methods, AIL methods, which either can use structured or unstructured meshes. They're sort of the best of both worlds. They take an Eulerian mesh, but they allow you to move them in any arbitrary way. Not in a fully Lagrangian sense. Well, they could if you wanted to. You could let them go fully Lagrangian, or you could keep them fixed. You can move the mesh somewhere in between a fixed Eulerian and Lagrangian. So it allows you complete freedom in how you move the mesh around. And that's what I would say modern moving mesh methods are really doing. They're a class of AIL methods. And AIL methods are also extremely popular in the engineering community. They're widely used in many other communities. So each of these methods has advantages and disadvantages. Each is good for a certain kind of problem. So for example, spectral methods, from an applied math point of view, they're beautiful methods. They have this exponential convergence. As you increase the number of spectral elements, the convergence rate goes up. So you have exponential convergence. But the problem with them is they don't treat compressible flows very well. Treating shocks and discontinuities produces Gibbs ringing phenomena. So they're not very useful for compressible flows. And so those tests I showed you yesterday of blast waves, very, very difficult to do with a spectral method. And I've mentioned some of the advantages and disadvantages of all these other methods. So the point is that no one problem is good for everything. This fixed structured mesh we use for Athena is good for some problems, but by no means is it best for all problems, and other methods might be much better. So maybe a bit more about Galilean invariance then. So, so in a recent paper introducing the Arepo code, Walker-Springel has reported that grid codes give you a different solution when you boost the solution by constant velocity. So as to say, the results look different when you run them in different frames of reference. So by adding a background constant velocity. So this, of course, violates Galilean invariance. If you add a constant velocity to the equations of motion, the solution should not change. The laws of physics are the same in any uniformly moving frame of reference. So this sounds like a big problem, and violating Galilean invariance would be a very, very big problem. So the simple way to sort of demonstrate this, and what the test that Walker shows, is the following. It's the Kelvin-Helmholtz instability run with two different density fluids. So I have a rho equals 2 fluid moving at half the sound speed to the right, sandwiched between a lower density rho equals 1 fluid moving uniformly to the left at minus the sound speed. So if you don't provide any perturbations, this is an equilibrium state. It'll just keep flowing past each other forever. But this is an unstable equilibrium. If you add a small perturbation, if you add a small transverse velocity, put it in a single mode, single sine wave, then that'll excite the Kelvin-Helmholtz instability, which is present between two fluids which are shearing past each other. And so that should generate vortices and rolls and cat's eyes. And so this is clearly seen at the bottom, where the calculation is done in a frame of reference which is stationary with respect to sort of the mean flow here. So no translation here. And you see indeed these nice KH rolls being developed at some later time, producing these little cat's eyes. But if you do the same calculation with the same code and the same algorithm, but you boost the frame of reference to equal to the sound speed. So now you're just solving the equations in a frame of reference which is moving to the right at the sound speed. Then it looks different. These cat's eyes are sort of going away. They're getting smaller. And indeed, if you boost it to a frame which is 10 times the sound speed, it looks like the KH instability has gone away completely. So yeah, it looks pretty bad. I mean, it looks like the KH instability has gone away. It certainly looks like the solutions are not the same. And it certainly looks like the laws of physics have changed. So the statement is that fixed grid codes produce solutions which are not Galilean invariant. However, this should worry us all, because if this were true, then of course Eulerian grid codes would be useless, because they would not satisfy one of the basic laws of physics. And the fact that they've been around for sort of 70 years means, gosh, why didn't anybody notice that these methods are totally useless because they violate the laws of physics? That should be your sort of first concern, that the statement seems really dramatic. Secondly, if this were true, it would violate one of the few theorems we have. There's very few mathematical theorems you can prove in the numerical analysis of hyperbolic conservation laws. One of the few theorems we have is called the Lax-Wendroff theorem. If you haven't taken a course in numerical analysis, I'd encourage you to, but you'll probably cover the Lax-Wendroff theorem. I'm not going to prove it in this short series of lectures, but that theorem states in a short and simple way that if a numerical algorithm is conservative, solves the conservative equations, it's consistent, meaning the discretization agrees with the underlying physics, and finally it's convergent, then it must converge to the correct solution. But we just said that the code's not Galilean invariant, so these two statements are incompatible. Either the Lax-Wendroff theorem is wrong, or the solutions are Galilean invariant. They both can't be true. So I think there's nothing wrong with the proof of the Lax-Wendroff theorem. Instead, it's a difference of interpretation of what we mean by solution and what we mean by truncation error in solutions is the issue here. And I think that if you say that the solutions are not Galilean invariants, then really that's a misunderstanding of the role of convergence and truncation error. And I would encourage you not to make that mistake yourself. So the key here is the Lax-Wendroff theorem says converges to the right solution. So in fact, if I just take a slide from one of, because talks are always online now, we can steal from each other, so I just stole a slide from one of Walker's talks, which makes this point beautifully for me. So this proves that Eulerian grid codes are in fact Galilean invariant, this slide right here. So let me explain it. What is this? This is a test problem, the Greshot vortex test. So this test is simple, two-dimensional vortex, an almost incompressible flow. So periodic boundary conditions. Set up a rotating vortex in the middle, lower pressure in the middle. The flow orbits around according to the pressure gradient, the radial pressure gradient. It's a stable, stationary flow, doesn't evolve in time. And so then you just evolve this numerically for some fixed period of time. Because it's an analytic solution, you then compare the numerical solution to the analytic solution, compute the L1 error, and then you repeat this at many different resolutions. This is just like doing the linear wave test. This is a great way to test codes. So you're just doing a convergence test on some two-dimensional problem. The solid line is second-order convergence, as you would expect for a second-order scheme. And then the symbols here are for a repo using a moving mesh, a fixed mesh. And then, in fact, he's used Athena to actually compare against, which is the triangles. And so for a flow which is not moving, if you're using a frame of reference which is stationary with respect to the vortex, then this is the dash solution. So these points here connected by the dashed lines are the convergence of the solution in this fixed frame, non-moving frame. And you can see that our repo and Athena are converging at both at second order and very, very similar errors. Now, if you then repeat this test and you boost it into a frame, moving at the sound speed or 3 times the sound speed, then you find that the moving mesh version of a repo, the errors don't change. But for the fixed mesh version and for Athena, which of course has a fixed mesh, then for any given resolution, the error increases in proportion to how fast you're moving it. But then it continues to converge in that frame at the same rate, second order. So at any given resolution, the error goes up, but it continues to converge in the second order. Similarly, if you're at any particular error and you want to get that error, you have to go to higher resolution if you're in this moving frame and using a fixed grid code than you would if you had the moving mesh. But the point is that every single case is converging to the same solution. The L1 error is going to 0 in every single case. If I continue this forever, they will all find exactly the same solution. If grid codes were not Galilean invariant, they would not be converging. They would not find the same solution at high resolution. They would find some other solution. And so that the fact that they're convergent means that they're finding the same solution, and therefore it's Galilean invariant. So question?
Could you rephrase that as a resolution criterion in terms of how fast the both motions are in your problem?
I mean, of course, for this particular test, you could take this data sort of to calculate what resolution you would need, but that would be a problem-dependent thing. If I did some other test problem like the KH test and I plotted these errors, it would depend on the precise nature of that test. So while you could do such a thing, I'm not sure it would be particularly useful because it would be a problem. Since the truncation error is a solution-dependent quantity, it'll change. The difference between the truncation error will change. So what's really going on here, and what this figure is actually showing, is the truncation error is different in different frames, not the solution. The solution is what you get when n goes to infinity. What's different is the truncation error in each frame. That's the difference in interpretation here. So is that a worry? Should we be really worried about the fact that the truncation error is larger in these moving frames? Well, perhaps. I mean, it all depends on your application. If your application is dominated by flow, which is very supersonic perhaps, and the largest source of error is advection in your problem, then reducing this error is a good thing because you're going to get a more accurate solution for the same cost. But of course, there's many sources of error in the solution, not just due to the motion on the mesh. For example, in multi-dimensions, there's a discretization error associated with unstructured meshes, which doesn't exist with structured meshes. And maybe the best way to see it is just take a picture of what a code like a repo will produce for some compressible flow. This is the blast problem I showed you yesterday. Set a blast wave off in the middle of the mesh, let it expand. Because the mesh is following the flow, then all the mesh points are getting compressed into the corners with the moving mesh method, and there's very few mesh points left in the middle. If I was concerned about following the Rickmeyer-Meshkov instability, remember those fingers you got when the shocks ran over the contact discontinuity? If I wanted to resolve that, I'd have a problem here because I have an unstructured grid with no points there. And moreover, this grid, it's very difficult to define multidimensional operators like gradient operators accurately, or I have to have lots of interpolation to calculate the normal directions to the mesh. And so there's a much larger truncation error in defining multidimensional operators in an unstructured mesh than in a structured mesh. So I'm not saying this is bad, I'm just saying it's different. I'm just saying that there's a larger truncation error associated with some operations and a smaller one with others, and it's all a matter of balancing. If advection error is your main problem, then yeah, this is a good thing. Moving mesh grid. If other sources of error are your main problem, then it may not be any real advantage. It all depends on the application. So should we be worried? Of course we should be worried about it, because we should always be worried about truncation error and all sources of truncation error. So to go back to the KH test, I mean, that's still a very dramatic picture and seems awfully convincing. Is that really just truncation error? So let me convince you finally that I think it absolutely is just truncation error. So what I'm really saying is that it's the truncation error that does not satisfy Galilean invariance, not the solution itself. The solution is Galilean invariant. And the fact that the truncation error changes the solution is actually, well, you're actually quite familiar with that. You're totally okay with that concept because you're all familiar with doing convergence tests. Forget about moving the flow. Just take this KH test, density 2 going one way, density 1 going the other, and solve it in a fixed frame, but just change the resolution of the calculation. You do it with a 400 squared resolution, you get all this complicated structure in the cat's eyes. You do it with 100 squared, you get what you saw before. That was the resolution used before. If I do it with 25 squared, the KH almost goes away. So hasn't the laws of physics changed with resolution here? I mean, shouldn't I be worried about this? This is no different than having boosted the solution in different frames. It's exactly the same phenomena. No, it's just because the truncation error is larger here. And so that's suppressing the KH modes associated with this shear layer. And that's what's changed the solution here. And you know, we all know that you have to run higher resolution, do convergence studies to know what the actual solution here is. And that's all I'm saying, is that if you have a rapidly moving flow, the truncation error could be important, and you might have to do a convergence study. In fact, if you just take the same test and you just change it a little bit, you just get rid of that slip surface. So a slip surface is when you have a discontinuity in the shear layer. But then there's no length scale to resolve there. There is a discontinuity, so there's an infinitely small scale. You can never resolve it. You can keep increasing the resolution of this test as long as you want. It'll never settle down to a fixed solution unless you add in viscosity or something else to break the scale. What you need to do is put in a length scale in the problem by making this not a discontinuity, but a resolved layer, a hyperbolic tangent function. It's a really, really sharp gradient, but it has a scale length A associated with it that you can resolve. And then do this test again, you know, supersonically moving flows, different densities, boost it into a solution. Let's not go for 10, let's go for 100. Let's make it really hard. Let's do a Mach 100 moving frame calculation with Athena, 10 times harder than the other one. And then let's do the solution in a fixed frame that's not moving and a fixed frame that's moving. And that's the answer. One of these solutions looks like the other. I don't know, maybe did you have Sesame Street when you were kids? One of these frames does not look like the other. Well, that's the solution. One of those is in the moving frame, and one of them is in the fixed frame. And yes, they're essentially exactly the same, because I'm able to resolve the solution now. And so when I have a resolved solution, the laws of physics, truncation error is not dominating the solution anymore. It's resolved. So you know, my code is giving me a resolved answer, and since the code's Galilean invariant, it gives me the same solution no matter what frame I'm in. If I tell you this was the one that was moving at Mach 100 and this one was moving at not moving at all, exactly the same picture. In fact, I can do much better than that. I can actually compute the linear growth rates. I can calculate the rate at which the transverse perturbation is growing in time. It should be exponential with this slope that's given by the linear stability analysis of KH instability. Plotted here are two lines, solid line, dashed line. One is Mach 100, one is the stationary. They're exactly the same. The error is the same in both calculations because I have a resolved solution. So I think that this, again, definitively says that once you get rid of this truncation error effect, that the solutions are. So it all comes down to the truncation error is different, not the solutions. So Galilean grid codes are, I have not wasted my entire career. Fixed Eulerian grid codes are Galilean invariant. That's it. Yes, truncation error is not Galilean invariant, but that's a whole other matter. We can, you know, debate that separately. Okay, so I will now get off my soapbox. Cylindrical meshes. Sorry, good.
How about the convergence for the low-length invariant?
Sorry?
How about the convergence
Convergence.
for the low-length invariant
For the Lorentz invariance?
in the special relativity?
What about special relativity? I'm not sure what you're asking.
My question is convergence
Yes?
for the low-length invariance for the Lorentz transformation.
Yes.
How
In a relativistic code,
Yes.
you mean?
Yeah.
I mean, I don't think any of the, from a numerical analysis point of view, nothing really changes. The equations of special relativistic hydrodynamics and MHD are a set of conservation laws. You can discretize them in the same approach we're using. You know, you can then, you know, look at convergence and truncation error in the solutions. You're worried that now Lorentz transformations between solutions can change the truncation error and the nature of the solution in that case. I mean, I think that's a subtle issue that perhaps you may have to worry about. For example, if you're trying to calculate some derived quantity in different frames, you'd have to worry about the role of truncation error in affecting that. But that's also true here, so I'm not sure it's really that much different. Okay? And yes?
How do you decide if the result are resolved or not?
There's a good question. How do you decide whether the results are resolved or not? I mean, I wish there was just a formula. You could say, oh, you know, if you calculate this number and it's greater than 42, it's resolved. But you can't do that. In practice, you have to do it experimentally. You have to try changing the numerical resolution and seeing whether or not the quantity that you're interested in, your application, is changing. Of course, you know, if the truncation error is affecting the solution in any way, it will change on a point-wise basis. The exact flow you get at different resolutions will not be the same. The density in this cell at this time will not be the same number to 16 digits in double precision as it would be if you had a different resolution. But maybe you're not interested in knowing what the density is in one particular cell at one particular time to 16 digits. You may be only interested in the PDF of the density or some other statistical measure of the flow. And that does converge. In fact, this gets to a more important issue, and most turbulent flows are chaotic, meaning that you can never get the same solution at some later time, you know, if you not only vary the resolution, if you vary the compiler and run the code again with a different compiler, you get a completely different solution at a later time if the flow is chaotic. So the only thing you can measure in a chaotic flow is statistical properties of the flow, averaged over a long enough time scale that they're no longer varying. And so you have to, as an application-dependent way, run different resolutions and measure the quantities you're interested in. Normally you say, well, I can't afford to run it twice. I mean, I'm already running at the highest resolution I can possibly afford. I can't do a resolution study. That would take 16 times more computer power to double it. Well, you don't have to always go to higher resolution. Go to lower resolution, half the resolution. If the solution doesn't change, you're safe. You've at least reached convergence. If the solution does change, well, you should be worried. Then maybe you really should have to go to 16 higher, and that's just the way there is, all you have to do. So there's no short and simple answer. It's your responsibility as an application scientist to report results that are reliable and resolved and not affected by the numerical truncation error. So that's just the way it is. Okay. So cylindrical. So this is fairly straightforward, I guess, and so I'm going to mostly follow a set of slides that Aaron Skinner, who is a graduate student at Maryland, working with Eve Ostreicher, who wrote the cylindrical grid extension of Athena for his thesis. I'm going to use a set of slides that he has put together and just follow along with what he says. And I'm just going to try to hit the highlights. What changes with cylindrical grids? Why bother to use cylindrical grids? Because although there's no complicated shapes in astrophysics that we need unstructured meshes to match to in general, there are certain symmetries. For example, disks sort of have a natural cylindrical symmetry. So cylindrical meshes match to disks, which are a very, very important object in astrophysics. Similarly, spherical polar meshes map well to stars. And so both cylindrical and spherical meshes are very, very useful for doing astrophysics of stars and disks in each case. So what changes with cylindrical coordinates? Well, the first thing that changes are the equations, but only in simple ways. So really the only equations that change much are the momentum equations. So these are the three components of the momentum equations in cylindrical coordinates: the radial momentum equation, the azimuthal, and the vertical in the z direction. And the only thing that really changes is you add a source term to the right-hand side of the radial momentum equation, due to the geometry of the flow, of the grid actually, the geometry of the grid, and then you add in some geometric factors into the operators in the phi component of the equation as well as the other two equations. But the fluxes themselves, these m's, are Aaron's way of representing the f, g, and h's that I wrote down before. Those themselves don't change. They're still the linear momentum fluxes. So I can still use the same Riemann solvers that calculate linear momenta, the m, and then plug them into the equations with the appropriate geometrical factors. So that's pretty straightforward. The beauty of this form for the second equation is that there's no source term on the right-hand side. This is a strong conservation law, right? It's time derivative plus divergence of a flux is 0. No source term. So this azimuthal momentum it preserves angular momentum exactly in this discretization. You can't do that for the radial momentum. That's not exactly conserved. There is a source term there. So that's one advantage of writing the equations this way. There's, of course, many ways to write the equations. You could pull these geometrical factors out. That would introduce source terms. But I think this way is kind of nicer because it's a strong conservation form for angular momentum. The other equation that has a change is the induction equation. But again, this is even simpler. There's no source terms in the induction equation in any component for the R, phi, or Z component of the magnetic field. And once again, the J's with the electric fields, I called them before, they don't change. So you can use the same Riemann solver, the same CT algorithm to calculate the electric fields at cell corners, the same CT algorithm to update it. You just have to add in the appropriate factors of R in the difference equations. Sorry.
But if we have external gravitational potential, R.
Yes. I mean, of course, if you add other physics to the problem, which includes source terms, then there would be source terms in the momentum equation. I'm considering the case of ideal MHD, the simplest problem, no extra source terms. That's right. So what other steps? So far, so good. I mean, very, very few changes. The equations have got some minor changes. Well, I sort of skipped over this corner transport upwind integrator last time because it's rather complicated, and going through it all in a lecture may not be the most productive way to spend time. But if you are interested in CTU and you're using it, then unfortunately using cylindrical coordinates with CTU requires substantial change. In particular, the reconstruction step, and I mentioned this yesterday in passing, the reconstruction step, when you're calculating the left and right states at cell edges, when you're using CTU, involves a time average, a time advance, using linearized systems of equations. So the reconstruction itself does a time advance. As soon as you start doing time advances, you have to worry about source terms. And so in order to do this time advance, you need to do a linear decomposition of the equations, and you have to calculate additional source terms for CTU in the reconstruction step. Another issue that I add here is a bullet on the bottom that Aaron didn't point out in his original slide, but I want to make the point of, that you have to also be very careful to distinguish between the geometrical center of the cell and the volume center of the cell. In a finite volume method, the quantity U is located at the volume center, since it's a volume average. And that may not be the same as the geometrical center, the distance halfway between the cell faces. And when you're doing a reconstruction and calculating the difference between U at I plus 1 minus U at I, what delta X or delta R do you divide by? It's the difference between the volume centers of the cell, not the difference between the geometrical centers of the cell. So that's a second order difference that will make a big problem at near singularities, where if you have a pole in your coordinate system near r equals 0, for example, the difference between the geometrical center and the volume center can be very large. So that's something you have to be careful for if you don't want to get features in your solution at singularities in your mesh. So Aaron wrote out this linearized system that you have to evolve. So the reconstruction step in CTU involves evolving this set of equations for the primitive variables W that you're going to use to construct the left and right states. This is the Rose matrix A. If you're familiar with the Rose matrix solver, you've seen it, Riemann solver, you've seen it before. The point is that the source terms in the right-hand side that you have to use to evolve these equations include some geometrical factors that weren't there before. So you got to go inside the reconstruction algorithm and fiddle with things a little bit if you have curvilinear coordinates. And these source terms are not needed in the Van Leer integrator, and so this change is not necessary there. But that is another example why Van Leer or Runge-Kutta time stepping in general, in fact, is kind of an advantage for more advanced physics, because you don't need to make such substantial changes. For example, adding curvilinear coordinates is somewhat easier in that case. So once you have the reconstruction step, if you put in the appropriate source terms, then you use the finite volume discretization to update the vector of conserved quantities Q. Here's the difference equations, and once again, it all looks very, very familiar. The divergence operator only has a geometrical factor that enters for one of the equations. But then there's this source term on the right-hand side, which we saw, for example, the radial momentum equation has a source term. So now you've got to calculate the time averaged and volume averaged source terms on the right-hand side to do curvilinear coordinates. So now we need a second-order accurate estimate for the time and volume averaged source terms. That's going to be a bit tricky. So how do you do that? Well, explicitly, what you need is this quantity m phi over r averaged over the time step and over the volume of the cell. So it's this quantity here. Now, notice that it contains quantities I already know at volume centers, because these are the quantities I'm evolving. For example, it contains momentum and density. It contains phi component of the magnetic field. These terms I know their time evolution from the finite volume update. But it also contains the pressure, which is not a conserved quantity and not something I'm evolving. I'm only evolving total energy. So the problem with this source term is getting a good estimate for the pressure, the time average pressure in the cell. And there's different ways to go, and what Athena does is it takes the pressure that we know at cell edges. In solving the Riemann problem, we're calculating the pressure at the cell interfaces, because the pressure is one of the quantities that the Riemann solver returns or computes. So what we know what the time average pressure is at the cell faces, and then we're just going to do an arithmetic average or appropriate average of the pressures at cell faces to calculate the pressure at cell center, and that leads to a second-order accurate estimate for what the pressure should be averaged over the time and volume of the cell. There are different ways to go, many of which are consistent to second order, but this is just what we happen to do in Athena. So usually it's getting this pressure source term that's tricky, because often you have a flow, for example, which is in rotational balance. You're balancing v phi squared over r with some other source term, and they have to agree exactly for the code to hold stability exactly. And so different discretizations of this source term can make a big difference in whether the code can hold an equilibrium state exactly or not. For example, a rotational equilibrium state. So it's worth taking care in how you actually treat that term. So then there's a bunch of test problems. For example, rotational stability. I mentioned this is one of the applications you can try. You just take a cylindrical grid. You put a rotating flow with different profiles of the angular velocity omega as a function of radius. So if the profile exceeds some critical value, it becomes unstable by the Rayleigh criterion to rotational interchange to instability. So for q less than 2, it's stable. Q greater than 2, it's unstable. And so you can test the stability boundary carefully. You can run calculations with different values of q, which corresponds to different rotational profiles in the initial state. And you can see that as you get to q equals 2, to 2 digits, 3 digits, it's either stable at 1.999, the energy associated with the fluctuations remains constant, or it's unstable at 2.01, it's growing in time. So you transition from really stable to unstable very, very sharply. So this is a good test, because able to reproduce an analytic prediction for an instability criterion, that makes a good test. You can do convergence tests. I always like convergence tests because they show very small errors in the method. If your solution's not converging, you know something's gone wrong somewhere. So this kind of test shows that you've got all the reconstruction steps correct, you have all the source terms incorrect, or you wouldn't get second order convergence to very small error values. You can do field loop advection. I'm going to sort of skip through these in the essence of time. You can do blast waves on a cylindrical grid compared to a blast wave on a Cartesian grid. Again, these are not analytic solutions, but they're just consistency checks that you get the same solution computed on a cylindrical grid as you do on a Cartesian grid, as you should, since the physics doesn't depend on the grid system you're using. And then finally, you can do actual applications. Kareem Sarathi, another grad student at Maryland, used Aaron's algorithm to study the magnetorotational instability. What you're watching is the magnetic pressure evolving in time in a rotating disk in full 3 dimensions. We're just showing you a cut through the equatorial plane here in the middle. Started off with a regular magnetic field pattern that had no net flux, but it's a very weak field, so it generates the MRI after a few orbits. So now it's actually fully transitioned to turbulence. In the regions that are magnetized, we have MHD turbulence. Now we start getting accretion because the MRI turbulence is transporting angular momentum. So you can see that in this region, which has no magnetic field right now, it's slowly shrinking because on an angular momentum transport timescale, the material is slowly accreting inwards, eventually eating this up completely. Similarly, you can see materials moving outwards a little bit to conserve angular momentum. You can just keep running this forever. You can then compare the structure of turbulence driven by the MRI in a global flow compared to local shearing boxes. This resolution here is high enough that we can take a little 1 scale height patch, and it has a 32 by 128 by 32 grid cells in it, which is typical of shearing box calculations, local shearing box simulations that people have done in the past. So we can extract little tiny volumes of this, one scale height volumes of this calculation and compare it directly to shearing box simulations and see whether or not they agree, whether or not global effects make any difference. This movie will go on forever. It's only halfway through so far. It demonstrates again the biggest challenge in doing numerics is you're discovering visualization and analysis. Making this movie probably took as long as running the code, as you're probably not surprised. Sorry?
Not longer.
If not longer, exactly.
So which is the boundary of the simulation?
Sorry?
The boundary of this.
Yes, you see the boundary. So we're using free outflow boundaries, so mass, momentum, energy, magnetic field is allowed to cross the inner boundary and disappear off the mesh. And so in fact, over the course of time, the mass of the disk decreases by a factor of 3, because most of the stuff just accretes inwards. And then that's the big problem about doing global MRI simulations is holding a steady state. You've got to add mass somehow, and that's kind of challenging. How should you add mass? That's a challenge. You got to look at some problem, some application where mass is being added in naturally. Right, Wendy? Yes. Okay, so my last 15, 20 minutes, is that right? 15 or 20? I think so. Let me say something about static mesh refinement. It's another aspect of the grid in grid codes. So there are many applications like the MRI and accretion disks where a static mesh would be very useful. We know that the midplane is where all the action is. That's where the disk is. That's where the MRI turbulence is most vigorous. So we like to be able to resolve small scales in the midplane. But in the upper layers of the disk, so this is a radial, azimuthal, vertical cut. So one little tile from a much larger accretion disk. So we'd like to be able to resolve the midplane of this disk much better than, say, the upper layers, the corona of the disk. And so that's where a static mesh would come in very, very handy. It doesn't need to be adaptive, it doesn't have to change, because we already know the midplane of the disk is located and it's going to be there for all time. It's not going to change in time. So static here is good. So there are 3 elements to mesh refinement, whether it be static mesh refinement or adaptive mesh refinement, that Patrick Hennebel already introduced, and I'm just going to emphasize again. There's 3 major things that you have to do with mesh refinement. Number 1 is prolongation. So at internal fine coarse grid boundaries, you have to interpolate the solution from the coarse grid to calculate the boundary conditions for the fine mesh. So again, just so everybody is on the same page, what do I mean? Here's my coarse grid. Perhaps I have a fine coarse mesh boundary here where I'm resolving this region at a finer mesh. This fine mesh cells need boundary conditions, but these cell centers on the coarse mesh are not, it's an unstructured mesh here. They're not lining up with this. So I need to calculate ghost cells for the fine mesh, which come from interpolating the solution on this coarse cell. And this interpolation has to be conservative. The sum of the conserved values in these fine cells has to equal the volume average value on the coarse grid. And most importantly, since I have a staggered mesh with CT, I'm going to have to interpolate the magnetic fields on face centers inside this cell to create the boundary conditions for the face-centered magnetic field used to update the fine mesh. So I need some kind of prolongation step that satisfies div B and calculates for me the face-centered magnetic field components on these Go cells for the fine mesh. It's the latter which is the hard part, because there ends up being more unknowns than equations in the interpolation step for the magnetic face-centered magnetic field. So there's various things you can do. We follow Toth and Rowe, which makes an assumption about the currents that are going to be in that prolongated steps to close the equations and produce a divergence-preserving prolongation step for the magnetic field. Again, I'm not going to go through the details. There's a very nice explanation in this paper, Toth and Rowe, of the exact interpolation formulas we use for the prolongation step. So prolongation is the first thing you have to worry about. Second thing you have to worry about is restriction. So you evolve this system of equations on this coarse and fine mesh, but there are overlapping regions between the coarse and the fine mesh. You're solving the coarse mesh in the regions where there's already a fine mesh solution known. And you always believe the fine mesh more than you do the coarse mesh. And so whenever you have a coarse mesh cell which is overlapped by fine meshes, you replace the coarse mesh cell with the average of the fine mesh solution. You believe the fine mesh more than you do the coarse mesh, so you always go back and replace all the regions covered by fine meshes on every grid hierarchy with the averaged fine mesh solution. So this averaging step is very simple. Good question.
Okay, so you're actually not computing any more values, like if you run this SMR and then you look at the BPM movies, you have to go into each region, you're not missing, where you specify higher mesh, where you're just averaging.
Are we actually, sorry, are you asking, are we calculating in the coarse mesh regions, or are we?
In the coarse mesh regions, you're just averaging what you already calculated.
That's correct. That's correct.
You see the full movement.
Exactly, exactly. It'll just overlay. There is a more subtle question here. Perhaps that's what you're saying. What you could do, here's a coarse mesh, and here's a region where you're covering it with a fine mesh. You could say, I already know that these cells I'm going to throw away at the end of the day on the coarse mesh. So let me just integrate the coarse mesh a few cells in from the fine mesh and leave a hole in the middle and not do the work here. Just calculate the coarse mesh with a hole in it and then replace it with the fine mesh. That would save you some floating point operations because I wouldn't have to be calculating things. We do not do that, however, because implementing this hole is complicated. And it's better just to waste the computer time to calculate that region, and then it's better in the sense that it leads easier to implement and is quicker, scales better and is a quicker solution than if you try to replace it.
These averagings, generally, are they simple average or weighted averages? Say, for example, mass weighted average.
They would be, in a Cartesian coordinate system, those are the same. In a curvilinear coordinate system, they have to be weighted averages, volume averages. So you have to take the total mass in the 4 cells and make that the total mass in the coarse cell, which ends up being a weighted average. Okay? Because the mass is not the same as density in a curvilinear. And magnetic field, face-centered magnetic fields, there's no problem here because all we've got to do is average together using area averaging the fine grid magnetic fields to the coarse grid. An important point about this is that this saves, when you implement this with parallel computers, this saves a huge amount of data to be passed. There's an instructive arithmetic calculation to do. Let me try to remember it here. When you think about implementing this mesh refinement on a parallel computer, you may say to yourself, it's important to make sure the fine mesh is on the same processor as the coarse mesh, because I'm going to have to pass data back and forth between the fine mesh and the coarse mesh all the time. I'm going to have to restrict the solution from the fine to the coarse. That's a lot of data to be passing back and forth. I want to make sure they're on the same processor so that data movement is minimized and it's very, very fast. In fact, that's a mistake. It's perfectly fine to have the fine mesh on a totally different processor than the coarse mesh and have to pass the entire fine mesh restricted solution to the coarse mesh. How do I see that? Well, imagine how much data movement you're already doing with MPI when you have these blocks of cells. So suppose I have a 64 cubed MPI domain. How much data am I passing between each 64 cubed MPI data domain? Well, I have to pass ghost cells on the surface of each surface of this domain. And with Athena, that's 4 cells. With a PPM code single step update, it's 4 cells. So I have to have 64 squared, which is the area of each face, times 4 cells, times 8 faces. It leads to 32 times 64 squared. It's only half the size of the entire mesh I'm already passing to just do the boundary conditions on a regular, unrefined mesh. If you then think about, well, suppose this was now SMR, and I have a 64 cube domain. I'm going to reduce that by a factor of 2 in each dimension in restriction. I'm only going to need to pass 32 cubed to the next processor. That's less data than I'm passing on the current level between processors. And since I already know that the amount of data, the time to pass data in Athena is extremely small, less than 1% of the calculation time, I completely ignore this. I don't need to worry about having the fine meshes and coarse meshes in different processors. It's not going to affect my performance at all. And so it gives me some much more flexibility in doing the MPI. And another important point to make here is this issue that this conservative average makes sure that the conserved variables are consistent between the different levels, not the primitive variables. They're not going to be the same. In particular, the pressure is going to be different, and the temperature is going to be different. Because what we're actually restricting is total energy. But the total energy is the sum of velocity plus internal energy. And since the velocity will be different on the coarse mesh than the fine mesh, usually smaller because I can't resolve small-scale features, so the velocity is getting washed out, that extra energy associated with the kinetic energy on the fine mesh will go into extra internal energy on the coarse mesh. So the coarse mesh is going to have a different pressure and a different temperature than the fine mesh. And if you're going to do microphysics like chemistry, I'm not sure if Paul's here, but if you're doing any kind of microphysics which is strongly nonlinear functions of the temperature, you have to be extremely careful. Danger, Will Robinson, danger. If you're going to do microphysics on the coarse mesh and the fine mesh and only restrict the conserved variables, that's not going to be correct, because the chemical reaction rates in the coarse mesh will be completely different than what they are in the fine mesh for that same overlapping region. What you have to do is restrict the chemical reaction rates. You have to calculate them on the fine mesh and then restrict all of that information to the coarse mesh to get the right chemical reaction rates in the coarse mesh. And that's difficult, swept under the rug, I think, a lot. But is necessary if your problem involves. Yes?
I just want to comment that there's the exact same problem if you have any cooling.
I'm sorry?
There's the exact same problem if you have any cooling.
Absolutely any microphysics that depends on the primitive variables, density, velocity, or temperature has a problem. Cooling, optically thin cooling is a problem. Rate of transfer, because the opacities typically are temperature dependent, so you'll have the wrong opacities and therefore the wrong rate of transfer in the coarse grid solution. So it could be a real problem if you're doing complicated microphysics with adaptive mesh refinement. You have to be very, very careful in making sure you're doing the prolongation restriction of all the things properly. Does everyone do that? Probably not. Okay, so we have prolongation, we have restriction. The last thing that's important is flux correction. So go back to these fine coarse boundaries. The amount of material that's leaving the fine mesh is the fluxes, given by the sum of the fluxes on the fine mesh cells. But the 2 fine mesh fluxes corresponding to the neighboring coarse mesh, they may not add up to the flux that was used to update that coarse mesh in the beginning, because they were calculated with different steps. The fine mesh fluxes were using a Riemann solver using left and right states calculated from the fine mesh, and the coarse mesh was using left and right states and a Riemann solver calculated in the coarse mesh. There's no way that those things are guaranteed to be the same. And if you don't guarantee they're the same, you're going to break conservation. You're going to have more mass flowing out of the fine mesh than is flowing into the coarse mesh. So you got to go back after the fine mesh update and take those fluxes from the fine mesh and compute the solution in all the coarse grid cells that abut all the fine mesh cells. And of course that ends up being complicated, because if you have a complicated sets of levels, then those boundaries of fine meshes can be very, very complicated. But it's an absolutely crucial step for conservation and for reducing errors at fine coarse boundaries, and especially complicated with CT. So this is one I would have to say, even I admit, this is where a staggered magnetic field is a real pain, because updating the magnetic field with CT at fine coarse boundaries using the EMFs from the fine meshes is getting quite complicated. So how do you test this whole thing? Well, you use the same test suite that's we're all using. You run all the same test problems as before, but you just use mesh refinement. A good one is you take this linear wave convergence problem I've mentioned a couple of times, periodic boundary conditions, uniform mesh, and you just throw down some arbitrary fine meshes somewhere in the domain, arbitrary shapes, arbitrary number. And then you run a linear wave over top of this mesh, and you have to make sure that there's no reflections. So you look for no features in the solution. And moreover, again, since this is a quantitative test, you can compute L1 errors. You can check convergence. And reassuringly, the L1 error linear wave convergence for this static mesh refinement versus fixed grid shows no difference. So you can be very confident that you've got all the flux. If you don't do the flux corrections correctly, it'll show up immediately. The static mesh refinement will not be converging. So this is a good way to test. It's quite a difficult test. It's not something you would normally do, run waves over top of your fine mesh boundaries, but this is a good way to test it. So finally, I only have 2 minutes left, so there's not going to be enough time. I was going to try to work my way through. I mean, I could talk a lot about implementation, but all I would be doing is replicating what's on the web pages. So I'll just go to this page. If you just go to the documentation page, which I'm hoping this would do if I did this properly. If you go to the Athena track pages, you go to the user guide, buried down here is this introduction to static mesh refinement, geometry of levels, configuring. You'll find out about exactly how we implemented Athena. There's lots of restrictions. It's not a very general package. There's things it can do and cannot do. And so, I was going to walk you through this, but I think in interest of time, I'll just let you look at it. Maybe the only point I want to make about this is one seemingly very restrictive property of the SMR algorithm in Athena, which is we use a uniform time step between all levels. So an additional complication I haven't spoken about that many AMR packages implement is that the time step on the fine mesh is half as big as it is on the coarse mesh. That's because the grid is finer, and so as Patrick Hannibal explained very nicely in his lectures, there's a stability constraint in integrating the equations. There's a limit on the time step, so-called CFL condition. The time step delta t has to be less than equal to, in one dimension, the grid spacing divided by the sum of the velocity and the largest wave speed in the problem, acoustic waves in hydrodynamics or fast magnetosonic waves in MHD. And so since the resolution is getting smaller, delta x is going down by a factor of 2 in fine meshes, it says your time step should be 2 times smaller as 2, and therefore you have smaller time steps. But that means that your solution is at different time levels between all the levels, so now you also have to interpolate in time when you're doing this restriction and prolongation steps. In Athena, we don't do that. We use the same time step on all levels, so there's no interpolation in time required. And that seems like a big mistake, except when you think about it, depending on your application, it's not. Because you see, the assumption that time step should get smaller when the grid gets smaller is based on this staying the same. It's assuming that on whatever level you are, the characteristic velocities are staying the same. And therefore, the characteristic time step's roughly proportional to the spacing. But that's not true with MHD. In fact, it's usually violated with MHD. The regions where the grid is coarse are the regions where there's not much material, which is regions where the density is very low, and that means that's the region where the alphane speed is very, very big. So go back to my accretion disk example. I showed you a picture. At the midplane of the disk is where I want to resolve it. The corona, the upper levels, is where I have the coarse mesh. But the largest wave speed by a huge amount is in the corona, because that's where the alphane speed's absolutely huge. So if I choose my time step on the finest level, if I choose my time step on the coarses level and then make the time step 2 times smaller all the way into the middle, I'm actually using an incredibly small time step on the finest level, and I'm wasting a whole bunch of computer time because I'm integrating the fine levels in a much smaller time step than I need to. So instead, that's an example where, in fact, a uniform time step is a much better match to the physics of the problem. And I think that's often going to be true in MHD. It's usually true that regions where the density is lowest is where you have a coarse mesh, and that's where the alpha speed is the highest. So I think using this uniform time step is actually a better way to go with many MHD problems. And it's certainly a lot easier to program and load balance and everything else. And so that's the decision we made for MHD.
It is quite efficient for hydro.
I mean, again, that would depend on the temperature profile. You know, if you're again doing an accretion disk, which actually has a hot corona, where the temperature is much higher in the upper layers than is the midplane, the sound speed would be much higher in the corona, and once again, the sound speed would be much bigger. So this kind of thinking is based on homogeneous, uniform flow. Of course, then that's true. But not all applications are like that, and so this doesn't always map to every application nicely. So I think that pretty much is it. So here's my summary. Once again, grid codes are Galilean invariant. Whew, good. Substantial changes are required for curvilinear meshes, at least with some of the integrators like CTU. Static mesh refinement is implemented in Athena, but there are significant restrictions and not all physics works. For example, the cooling and the chemistry and all that kind of stuff is not really working because you've got to do all that carefully with the prolongation restriction. What's coming up in the future will be more generalized curvilinear coordinates so we can do GR, and there will be an AMR package implemented the next year or two for another project we're undertaking starting soon. So that's what's coming in the future. And I'll quit here. Thank you.
For the cylindrical coordinates, is it possible to have the inner radius equal to 0, or do you always have this component?
It is possible to have the inner radius equal to 0. You do sometimes have to worry about exactly how you treat boundary conditions. I mean, it's not recommended or ideal because the grid cells will be extremely small in that very first radial strip of cells. There'll be very, very tiny pi wedges, and therefore the CFL condition for the transverse direction will be extremely tight. And so if you have a uniform mesh in cylindrical coordinates, the origin can be very, very restrictive in terms of the time step on the overall calculation. So if you can avoid r equals 0, you really want to. But if you really need to do r equals 0, you can do it.
Has someone done, so if you didn't have this phi direction, if you just had a collapse situation, is that possible?
Two-dimensional r phi or rz. I think there's
Neutral rotation if you instead were interested in like a spherical collapse.
spherical polar grids, basically. Yes, so there is a new spherical polar version of Athena, which is not in the trunk in the public distribution, that in fact Kengo Tomita, postdoc at Princeton, has recently implemented, following all the same steps but changing the cylindrical terms to spherical polar terms. So there is a spherical polar grid version available. It might, if it's fully debugged and working well, then we'll upload it to the, I don't like to put things on the web that I'm not absolutely sure work. And even then, there are still problems. I'm not going to say that everything on Athena works, the public version, but I try at least to think it works. So it's not ready for prime time yet. It's not in the public version yet. I think I'm a little over, so I better quit here. Okay, thanks.